All right, so we're going to use what we know about our trig functions to find the lengths of the missing sides of this triangle here. And so we're looking for a couple of things, right? First thing we're looking for is it a right triangle? If it is a right triangle, then that's going to allow us to use these trig functions to help us. So it is a right triangle, and that's because of this little symbol in the corner there showing that that's a right angle. So because of that, we know we can use sine, cosine, and tangent. And there are other situations out there where you might use those too, but right now we're sticking to the idea of a right triangle. Okay, so now that we know that, well, we can use what we learned about sine and cosine to help us find these missing two sides. So let's focus for a minute on this side right here. Let's say we're trying to find that side. That side is opposite the 30-degree angle. And so what I want to know is, what is its length? Now, in my experience with a right triangle that has a 30-degree angle, I know something. I know that the relationship between an opposite and a hypotenuse side of a right triangle has a specific value. And that value is 1/2. So since I know this from the previous video, I can apply that here because what I'm trying to do is say, well, I have a side that I don't know, and we'll just say that that's x, that's the opposite side, and I'm going to compare that side to the hypotenuse. But I need a value to compare this to. I know that in every other situation I've encountered with all right triangles, in this situation with a 30-degree angle, this relationship is equal to 1/2. And so now I can use this to solve in this situation. You could use algebra here, right? I could multiply both sides by 27, okay? So times 27 on both sides. And now x is equal to 27 over 2. Or, if you really want to write it as a decimal, 13.5. So that helps us now. Now I know that side. And the reason I know that is from past experience. I know that the relationship between the opposite side and the hypotenuse of a right triangle is 1/2 if we're talking about a side opposite a 30-degree angle. And remember that another way to say this is just to say this. Okay, let's try this again, but with the adjacent side. I'd like to know what that length is, and it's the side adjacent the 30-degree angle. So I'm going to think about my past experience and what I know about adjacent sides as they are compared to the hypotenuse. So we know that, again, in a right triangle with a 30-degree angle, the side adjacent to the 30-degree angle is approximately 0.866 the length of the hypotenuse. So I'll do this again, but this time I'll be using the adjacent side. So I know that I'm trying to find x, and I'm going to use the relationship to the hypotenuse as a starting point for how I can find x. So I'm going to think about what I know about the relationship between adjacent and hypotenuse sides of right triangles, and I know that in the past it's approximately 0.866. Now this is rounded, so we're going to want to get away from using rounded numbers, but I'm just following from the previous video what we just did here. And I know that it's approximately that, so maybe I'll just say approximately here to be accurate. And so to find x, all I have to do is multiply both sides by 27 times 27. So I'm going to find that x is approximately, and I'll do the calculation here, times 27, 23.382. Now, this is approximate. I know that that's this value here. So I should start being totally accurate. We know that instead of writing this, we could write this. And that's what we'll be writing from now on, because the reality is we don't actually care what this number is now. It doesn't really matter to us so much. We just have to be able to express that in such a way that a calculator is going to be able to give us a final answer. So from now on, instead of writing all this, the side adjacent to the 30-degree angle is approximately 0.866 the length of the hypotenuse, instead of writing all that, I'm just going to write cosine of 30. And the calculator knows what I'm talking about. The calculator knows that I'm comparing the adjacent side of a right triangle to the hypotenuse of a right triangle from the perspective of a 30-degree angle. And it's all boiled down into that little formula. So now let's do some faster examples. Okay, I would encourage you to pause the video and try to do this on your own ahead of me, but I'm going to walk through the process here now. So I'm asked to find the lengths of the two missing sides. This is very similar to the previous problem that we just did, except we don't have a 30-degree angle. So we can't cling to those values that we memorized maybe from doing so many examples with a 30-degree angle and a right triangle. Now we've got a 57-degree angle. So we need to think about the fact that our opposite side is now this side. All right, I'm just going to call that O, I guess. And then our adjacent side is now this side. Okay, so I'm now looking for an adjacent side and an opposite side, but the perspective has changed a little bit compared to some of the previous triangles that we've looked at. Let's focus on O for now. I want to find the length of O, and I'm going to be comparing that length to the hypotenuse. So what I'm doing here, and I'll just write another little equation over here, I am comparing the opposite side of a right triangle to the hypotenuse side of a right triangle. So I'm keeping this fraction in this exact same format as I continue here, and I'm going to write another thing to the left of it. What do I know about that relationship? Well, I don't know this value off the top of my head, but I could ask a computer, what is the relationship between the opposite side and the hypotenuse of a right triangle from the perspective of a 57-degree angle? And all of that can be said by just typing this into the calculator. The calculator is going to give you a value. It doesn't matter what that value is necessarily right now, because this isn't the final answer to the question. This is just a number that's going to help us get to the final answer. All right, so we don't need to tie ourselves to this part of the fraction here necessarily. So that doesn't need to be there. It's really about this equation here that we're trying to solve. So I could write a decimal here, but I know that I would just be rounding, so I'm not going to do that. I'm just going to solve this just like I would if I knew the number there. I'm trying to get O alone, or that missing side if you want to call it X. So I'm going to multiply both sides by 9. And now my equation says O is equal to, and I'm just going to write the 9 out front, 9 times sine of 57. Or in other words, 9 times the relationship between the opposite and hypotenuse side of a right triangle from the perspective of a 57-degree angle, which is a mouthful. So you can see why people stopped saying that and started saying things like this. This is a much better way for us to express that. So this is what I'm going to type into a calculator. And when I type that into a calculator, I'm going to have a very close guess. Because, again, I'm not going to write every single number to infinity, but I'm pretty close here because I did use the exact relationship between the opposite and hypotenuse side. And I get 7.548. And I could keep going because it's a non-terminating decimal, but I now know that this side here is approximately 7.548. Let's do the same thing for the adjacent side. So we'll set up a similar equation. I know that adjacent sides, if I compare them to a hypotenuse, are always going to be the same. It's always going to be the same comparison. As long as I'm in a right triangle with the same angle, it's going to be the same proportion every single time. So I'm trying to find this adjacent side as compared to this hypotenuse. So I'm going to ask a calculator, what is the relationship between the adjacent side and the hypotenuse side of a right triangle from the perspective of a 57-degree angle? But I'm not going to write all those words. I'm going to write cosine of 57 instead. And I'm not going to write the actual value there because there's no point in doing that. It's going to be a non-terminating decimal most of the time when you do this, and so you don't want to round at this stage in the problem. So I'll get rid of this. I don't need that there. That's just to help me remember what I'm doing. And now I'm going to get A alone. Times 9 on both sides. So A is equal to 9 times cosine of 57, or 9 times the relationship between the adjacent and hypotenuse sides of a right triangle from the perspective of a 57-degree angle. So I just need to type that into a graphing calculator, make sure I'm in degree mode, because notice this angle here is given in degrees, and I'm going to get approximately 4.902 if I round to the thousandths place. Okay, now we've got all our sides. Just to check and make sure that this is consistent with what we found in the first video when we were defining sine, cosine, and tangent, let's make sure that that tangent relationship still holds up. So if you type into a calculator that tangent of 57, or you type tangent of 57 into a calculator, you are asking the calculator what is the relationship between the opposite side and the adjacent side of a right triangle from the perspective of a 57-degree angle. So let's see what that is. And if you type that into a graphing calculator, so tangent of 57, make sure you're in degree mode, you get 1.539. And since there's an 8 after that 9, I do need to round that 9 up to a 10. So I'm going to write 1.540 is our rounded value here. Let's make sure that this holds true in this example. So let's take this O value, 7.548, and divide it by this A value. Instead of using just generic O and A values, we'll use our actual O and A values and confirm that this relationship holds true still. So let's divide 7.548, remembering that these are rounded numbers, by 4.902. And this ends up being approximately 1.540. So our relationship still exists with tangent. So we still have these same relationships taking place between opposite, adjacent, and hypotenuse sides of the triangle, and we have a way to express any one of those just using those three trig functions. Now let's do some quick examples. So in each triangle below, solve for x. There is an x in each of these problems, and I'm encouraging you to pause the video and solve it. And now I'm going to assume that you've already done that. So let's go ahead and find the value of each of these x's in each problem. So the first thing that I need to identify is in each case, what is the relationship that I'm going to be examining here? So here's my 31-degree angle. It's a right triangle, so that's good news. I can make sure that I'll be using sine, cosine, or tangent here. And it looks like the two sides that are relevant are the opposite side of that 31-degree angle and the hypotenuse side of that 31-degree angle. So I'm going to think about what I would have to tell a computer to get it to understand that I'm looking at an opposite and a hypotenuse side here. And I'm going to be using sine because that's what we've used in every case in the past. So I'm going to be telling the computer to use sine of 31. Now I don't care what that value is, but the computer is going to know when I type in sine of 31 that I'm examining the relationship between the opposite and the hypotenuse side of a right triangle. So I'm typing sine of 31 into the computer. And I know that in my case, that's the same as saying x over 11 because x is that hypotenuse side and 11 is that hypotenuse side. So paying attention to this equation right here, I need to get x alone. I'm going to multiply both sides by multiply both sides by 11. All right, times 11. And 11 times sine of 31 ends up being approximately 5.665. So that is my best guess for x. That is a very close approximation. And if you're working on a worksheet for a homework assignment, just pay attention to what they're asking you to round to. In this case, I've rounded to the thousandths place. Let's go ahead and do number 2. Number 2, it looks like from this 44-degree angle, I am looking for the adjacent side, and I've been given the hypotenuse side. So I'm going to be wanting to use a function that compares the adjacent side to the hypotenuse side of a right triangle. I know that that function is cosine. So I'm going to ask a calculator, what is the relationship between the adjacent and hypotenuse sides of a right triangle from the perspective of a 44-degree angle? And I'm going to compare that to what I know about this triangle. All right, so to get x alone, I'm just going to multiply both sides by 17 times 17. Those cancel there, times 17. So what is 17 times cosine of 44? Approximately 12.229. That's the length of x. All right, third example. I have a 7-degree angle. Okay, so this is 7 degrees. And it looks like I'm going to be looking for the opposite side and comparing it to the adjacent side. So I need a function that compares the opposite side of a right triangle to the adjacent side of a right triangle. I know that function to be tangent. So I'm going to ask a calculator, what is that relationship in a right triangle? And I'm going to compare that number to my opposite side divided by my adjacent side. So when I solve this, times 10.7 times 10.7, I'm going to type 10.7 times tangent of 7 into my graphing calculator, and I get approximately 1.314. So that is the approximate length of that side based on what I know about these relationships. Okay, so we're starting to shorten the vocabulary that we use here. I'm no longer writing a whole sentence saying, what do I know about previous triangles where we have a 31-degree angle and we're looking for the opposite side compared to the hypotenuse side? Don't have to write that. I can just write sine of 31.